Hi, welcome to this episode in which we will talk about how to do ERP analysis on EEG signals. ERP stands for Event Related Potential, and we will see how to perform this kind of analysis on our EEG signals. And we are still using the data from BCI competition IV. But in the ERP analysis, it will be slightly different because here I'm going to use this on the simulated data. So everything else is using our data from the PCI competition, but here I'm using simulated data. And the reason for this, I really want to emphasize some differences between conditions. So I'm going to use simulated data because with this data, I didn't find a very prominent effect on the ERP level between conditions. So I decided to go with the simulated data, and in the meantime I would really take this chance and just talk about one of the functions of LV that we can use to simulate our data, and I think it's very handy to use this function. In the last time we were doing manual cleaning, so we'll be going back to this data after cleaning and use it with other analyses. But with the analysis of the ERP, we're going to use simulated data, as I said. So let's access this function and see how we can use it to generate data. I think I briefly talked about this function in the Fourier transform video, but in this one I can go over it very quickly again. And the main idea is that we are drawing a signal by hand, and the idea is that we want to convert this drawing into an actual signal. So we basically take the minimum and the maximum of this, we resize our drawing, and also we start by thresholding our data to just know the positions of the plotted signal. And then I do this in a loop by defining different black and white connected points, basically. So the thing is, I need to draw many signals, not just one signal, and I put them underneath one another such that we'll have rows of many signals, and then the columns will be the time samples. So let's try to do this. So it always acts on this drawing to PNG, which should be always located in the same folder. This is the one, it's a drawing, and if you remember, that was the signal that we had in the Fourier transform video. So in this one I'm going to change this, and we want to have many signals underneath each other. So let's say that we have 5 signals. So let's say that this is one signal, 3, 4, and 5. So the thing is, what I'm trying to do here, I'm trying to simulate some data. I'm assuming that this is the onset of my stimulus, and assuming that there is an ERP, there is an event related potential. Basically, it comes from the name. There is a change in the amplitude, and it's related to this event here, the stimulus. So it's really obvious that we are talking about time domain signals, and we are looking at changes of this time domain signal in response to some stimulus or any kind of stimulus that we might have. Okay, so right now I'm just gonna save this. Okay, and let's remember this shape, because right now I'm gonna read this and put it in signals. So let's execute this line, and as we can see here, I'm plotting using this line. I'm plotting all the signals, and also I'm specifying the number of samples that I need to draw my signals with. So basically we are drawing all of our signals with a unified length of 100 samples, and we can see this. We have drawn all of them on top of each other, and we can see that there is a change here in the ERP. So that would be our first like 5 signals. And here we can assume something. Actually, we can assume that this is like an ERP for um, doing task A, okay, and we want to differentiate between this condition, between this task A, and another task B, okay. So I'm gonna assume that we have task B. I'm gonna draw some signals for task B, and I'm gonna assume that the ERP during this time will have the opposite effect, so it will be going negative, okay. So I'm gonna draw other 5 signals and assign them to signals 2, and signals 2 will be our second condition. So the thing is, when we run our ERP analysis, we will be trying to look at the differences around these times here, okay. So let's go for signals 2, and for that I would need to update my drawing. So let's draw some signals by hand. Okay. 3, 4, and 5. Okay, and I'm gonna save this and then just run this line, and we can see nicely that now we have our signals. Right now I'm aggregating all my signals here. So signals here is aggregated and ready. I'm gonna put this in a different cell such that I only run this part. I'm gonna place a breakpoint, and I'm gonna press F4 to run this block, or Control Enter, and then we can step together and see how to trace such code. Okay, so I'm just clearing a variable that I was using before. That's fine. So okay, here I'm loading LV layout, which is basically something that I talked about in the cleaning, and it's a layout identifying the labels that we use in our topography, so basically the name of the channels, and it also identifies the positions of every channel, which comes of course very handy when we are trying to do ERP analysis in a very nice visualized way, such that we put the ERP outcome of every channel in the respective position of this channel, and we will see this in a moment. So instead of just aggregating, let's say, all the channels and looking at the grand average effect, I wanted to do this ERP analysis such that we can look at the condition differences on every channel, and we plot this ERP in the position of that channel. So it will be very handy to look at the complete effects like that. Here I'm just putting the signals, and basically because our signals was just times, just signals, here I'm just putting this into 58 channels. So I'm just repeating this signals. I'm repeating signals inside a lot of it channels, such that we will have our golden tensor of trial channel time that's inside them. So that's trial and channel and time. And then I'm just adding some fields to our main struct. It will be is data. So I'm adding the data itself, the trial, and then the trial info, as we discussed before, is identifying the conditions. So basically we have our first 5 signals to be from condition 1, and the other 5 signals to be from condition 2, and that's what I'm doing here. And then I'm defining the time dimension, and it will be from 0 to 1 second, and of course of steps of 1 over the sampling rate, as we said in many tutorials before. So that will go from 0, and it will have 100 samples, and will go until almost 1 second. Okay, so then I'm defining the layout, I'm defining also the labels, and we can jump right ahead and look at the LVERP script. So this will take basically the trial info, time, layout, and label. This would be the kind of struct that this function is expecting. Okay, this will be our first thing that we pass to this function, and then we pass 2 flags. The first flag is a Boolean value specifying whether you want to do stats or not. So basically, would you like to do a cluster based permutation on your data? And we are gonna come back to this point and discuss how to do cluster-based implementation for ERPs, and we are going to use parametric using FieldTrip parametric correction, and we are going to use non-parametric using MVPA and see the differences between the outputs, and we will discuss this in detail. And the third thing that we pass to this function is the DoPlot. The DoPlot is basically whether we want to plot the outcome or not. And in this one, I just wanted to calculate the ERPs. So I'm passing my trials and I want to calculate the ERPs. The ERPs are basically calculated by averaging the signals together. So to calculate the average ERP or the ERP of this, we take all of these trials and average them together. So we basically look at the average of all of that. That would be our new that would be our ERP, and then we go to the second one, the third one, and so on. And this one as well, we take the average of all of the signals such that we create an average signal representing our ERP. Okay, so this should be what this function is doing, and there is an important detail that we might use a period before the stimulus, and we use this as baseline. Okay, so we might use a baseline period, and this baseline period is actually nice to have, because if you know what kind of a scale you had before the stimulus, it will be nice to get the average. So we basically average this in time such that we end up with one column, and then we subtract this from every sample. So basically we take the average of this, you will have one data point, and then you subtract this baseline from every sample. And this is nice because the baseline is basically some period in time that you guarantee that there is no activity relevant to the task in hand. So basically, if the participant is doing task A in these 5 signals, or task B or anything, you should guarantee that this baseline doesn't have task A being performed during this duration. And you take the average of this and you just subtract it. Okay, and that's nice because then you are eliminating any scaling artifacts from your data, and you will be really looking at the task differences when you compare condition A or task A to task B. Okay, so after doing this, we can access our function and trace it together. So here I'm doing just printing, and here I'm checking the arguments and just assuming if there is no argument set, what kind of output I will be displaying. But here we are setting all the arguments, so it's fine. Okay, so here I'm just storing my data, and this is a variable argument input. Okay, so that's when you have when you didn't specify the number of arguments of this function, MATLAB can just put this in a variable arguments. You can pass as many arguments as you'd like, and here I'm just accessing each one of them because I know that we have passed 3 arguments. Okay, and I'm loading LV layout. Here I'm converting to 3D to our golden tensor if the data was not in 3D, and here I'm interpolating the channels locations. And this step is quite important because if we want to plot our ERPs in the respective channel locations, we would need to change the original locations into something else, something normalized. So I take the positions and I look at the minimum and maximum and try to blend them inside of my main figure, okay, such that I end up with some normalized channel locations. Okay, and these will be important when we try to plot our data. Okay, I'm passing them when I'm plotting the data. Here we are differentiating between 2 things. whether we are working on the participant level, so the subject level, and we say that this is level 1. This is basically like a convention for naming this kind of analysis. So you might say it's level 1 or level 2. Level 1 basically when we are thinking about participants, level 2 when it's on the group level. So here I'm doing a small trick whether we have a trial info, because if we have a trial info, this means that we have many trials, and if we have many trials, this means that we have one participant, because one participant would have a lot of trials, as we see. So one participant data will have many trials in the first dimension. But if we take the ERP, so that's the nice thing about this function. You can pass the level 1 like stats or the level 1 data, so you can pause different trials inside a trial, or you can call this function twice. So after I call this function to calculate the ERPs, I'm going to aggregate the data from different participants and call this function again. So this function can differentiate between whether we are going with one participant. If we are going with one participant, then we are going to average the trials of the respective condition, and if we have many participants, then we are going to access the group level statistics and proceed with the statistical analysis of cluster based permutation. So right now we have trial info, right? Because we are having this trial info identifying the conditions, like identifying the trials, and here I'm just checking the conditions that we have. I'm taking the unique of the trial info. Trial info get 1 and 2, so the unique of that will be 1 and 2. And then here I'm assuming that I don't have any baseline periods, so there is no baseline. Okay, and here I'm checking if there is baseline. I'm gonna take the mean in time, as we said here. So I'm gonna take the mean in time, and I'm gonna repeat this in a matrix, and then go ahead and subtract this. So basically I will take the mean and I will repeat this column to match my data, and then I'm going to subtract the two of them from each other. So I'm going to subtract basically the baseline from the actual data. Okay, so here we enter the part after this, and what this is doing is basically putting the mean of the first condition, the trials of the first condition. So basically the first 5 trials, we're going to average them together, and we're going to put this in the first dimension of our ERPs, and we are going to average the second condition. And I'm doing this ERP for 2 conditions actually, just to keep in mind. And we're going to put the mean of the second one in the second row. So now we would have this variable, it's containing our ERP of the 2 conditions. Okay, and after doing this, we're going to just return from this function. So now ERPs got our 2 conditions, 2 ERPs, and 58 channels and 100 time points. So after doing this, we are gonna assume that this is the same data from different participants. So I'm just gonna repeat this for different participants. So here I'm just putting this inside ERP stamp. It's the same thing. Here I was just taking this from another port where I was doing different analysis. So here it doesn't matter. It's just storing this inside another variable. And then what I'm doing here is that we know that the first row is containing the ERP of the first condition, and the second one is containing the ERP of the second condition. So what I'm gonna do, I'm gonna repeat this 30 times, such that we will have 60 right now. So I'm gonna repeat the rows, and ERP, this function LVERP, knows that the odd indices belong to condition 1 and the even indices belong to condition 2. So that's what we are doing here. So by repeating this, I'm assuming that we had many participants, and we are putting each one of them will have two, so we are putting them underneath each other. So if we have 30 participants and each of them got two ERPs for the two conditions, then we would have 60, and then we can check this and we can see that this indeed is 60. And then we go again to LVERP, but this time we are going to do some plotting. We are going to plot our ERPs such that we can see the differences between conditions, but here I'm not doing statistics still, so I'm putting this as 0. So here we have entered the function again, but this time is different because this time we are having participants, so we don't have trial info, as we can see, and we have the ERPs, so that's nice. So right now we enter the group level stats. So right now we enter the group level, and we can use this other function that I'm not going to talk about, but this function is really handy in plotting the ERPs and plotting time frequency analysis and other things. But the main thing is I'm not gonna explain this function for a reason, that this function has a lot of lines like that I tried to use in order to make the visualization of data cleaner. So I'm not gonna go through all of them, and feel free to check them, and if you had any questions, please feel free to contact me. Okay, so we can go and execute this, and we have called this function, and we can see the output of that, which will give us two figures. So this would be the first one, and we can see that it's nicely drawing the average of our signals on every channel, and we have the labels of every channel, and it's the nice thing is we have a ERP on the respective position. So if we look at this, that's the actual topography, so we can see what is happening on every channel. Here of course all of them look the same because I have just repeated my signals in all channels. And we have a second figure, and this figure is very handy because with this figure, what I have done with this, I have used of course some FieldTrip functions, but I have also included something different, which is making this figure interactive. So basically you can, if you looked at your data and you found some channels interesting that might have the effect that you are looking for, perhaps the channels were central for instance, so you can just do this. You can mark the channels that you want to have together, and you can click on them, and this will produce another figure of the mean of these channels, okay, which is I think is very nice. So it's, you still have the chance to do this many times. It's up to you, so you can average all of them, and this will produce another figure and tell you that this is the grand average of all channels. And the nice thing about this kind of interactive analysis is that when we do statistics, you will be able to just on the fly basically repeat all of your statistical analysis by just pressing this. It will repeat the statistical analysis for the channels that you have chosen. So you will be able to, instead of going to the code, to just visually inspect your data and just to try to explore your data. Of course that's all exploratory, and just to see where the effect is coming from. So I think this will come very handy. Okay, so and then we go outside of this, and this would be everything for our ERP analysis. And feel free of course to use different data sets from actual data and test this. And by the way, you can do stats if you would like, but I would come to the tutorial of explaining the ERP analysis, or the basically the cluster based permutation for ERP or any kind of data that has this curve shape. So it could be actually for classification or any kind of signals that you would like to do cluster permutation for, but this will be in a upcoming video. So thank you so much for watching this video, and see you later.